Thank you very much for that introduction, and thanks for having me here. Yeah, as mentioned, I'm Fabian Orland. I'm from RWTH Aachen, and I'm here to present our work on correctness and performance analysis of an open source CFD application. And okay, yeah, perfect. The motivation for our work is basically that we wanted to conduct a performance analysis of the open source CFD application, which is called Calculix, which in the first place is a code that was mainly developed to solve structural mechanical problems using finite element method, but has then over time been further developed to also allow the solution of CFD problems, and therefore they implemented the finite volume solver basically. And as you can see, the code is a mixture between C and Fortran files, and to parallelize the code, they used pthread so far, so there's no MPI involved, just multi-threading. And what was the interesting issue with that code when we got it in our hands was basically that it showed very undeterministic behavior, which we found out was related to an undeterministic convergence behavior of the internal GMRS that is used to basically solve sequences of nonlinear systems that arise from the conservation laws, from Navier-Stokes equations, for example. And yeah, and we were wondering, okay, why is that? We had a look into the code and we did not find anything regarding something like random number generation or anything that would explain why the code behaves undeterministic. So what our solution was then basically, okay, we have to perform a real correctness analysis using, in this case, thread sanitizer, which you can easily enable for your own codes as well. If you add this compile flag like fsanitize equals thread, and this is supported by all of the recent GNU Intel Clang compilers. So if you have any issues, you can just use it and it will tell you where the issue is, hopefully. But before we can dive into the correctness analysis, we have first to learn about how the parallelization inside Calculix works, because it's a little bit complicated and it will be easier to understand the next slide if we first understand how it's parallelized. And here, so basically the parallelization, it's the same pattern all over the code for different purposes. In this case here, we will look at an example how the residual is calculated when the momentum equations are solved. And what they usually do in Calculix is they start with some C function, which in the end also always has this main suffix in its name. And in this case, what this routine always does is basically it has this loop structure here where there's a variable num CPUs, which basically indicates, okay, how many worker threads should be created. And then inside this loop, as you can see, the pthread create call is called, and it will create as many threads as the user basically requires by setting this variable. And then, as you can see, there's a function pointer passed to this pthread create call, which is another wrapper function also implemented in the same C file in the end, which basically then takes care of the work distribution. So in this case, it just calculates, it knows, okay, I have a certain number of equations that need to be solved. And then it knows, okay, I have this many threads. And then it just sets up the correct number of equations for this specific thread. And then afterwards, the actual computational work, for example, I don't know, some linear system solve, whatever. In this case, it's just the computation of this residual vector, or in the end, the norm of this residual vector is then carried out in some Fortran kernels. And then in the end, if the parallel work has been finished, then the main thread will use pthread join again to basically wait for all the parallel threads and then continue in serial until the next, let's say, parallel kernel is found in the code. And this pattern has a problem, especially for performance tools, because as you can see, it will basically, each time there's a parallel some parallel computation in the code, it will create new pthreads, but do not reuse the already created pthreads. So for example, when we executed the code and wanted to just simulate 5 time steps using 8 threads, the total number of threads was then almost 4,000 that were created over the whole runtime. but at one point in time, there are only 8 threads will be used, right? So this does not really make sense. And especially for performance analysis tools, this is very prohibitive behavior because, for example, the X-Ray tool, which is developed at the Barcelona Supercomputing Center, which allows you to collect basically performance data from your code. It was only able to handle up to almost 8,000 threads, and then it crashes. So we were not really able to perform any larger runs than, for example, 5 time steps. But coming back first to the correctness analysis, as I said, we use thread sanitizer for it, and if you execute your application after it has been instrumented by thread sanitizer, you will get output that looks a little bit like this. And first of all, it looks like some wall of text, and you may ask, okay, what does this wall of text tell me? So first of all, it will tell you the obvious conclusion that it found a data race in your code. And in this case, the data race is caused by 2 concurrent writes to the, of course, same memory location. Otherwise, it wouldn't be a data race. But thread sanitizer, as you can see, it has much more information in it. And it can, for example, first of all, it can tell you, okay, these are the 2 concurrent writes. One was performed by thread 2, the other one was performed by thread 1. And in terms of the memory location, it knows, okay, it was a location of size 64 bytes. In this case, it knows the address. And also it has, as you can see below, the whole stack trace basically where this block was finally executed, not executed, allocated. And for example, coming back to the parallelization code from before, we know, okay, it was actually the conflicting variable was allocated at this line. It's an array which has as many elements as there are threads. And then basically following the whole parallelization pattern that we discussed, this variable gets passed down the stack until it basically gets passed into the Fortran code here. And then inside the Fortran code, there finally the data race happens because both threads simultaneously want to execute this variable res to initialize it with 0 to calculate the actual residual. And as you can see, thread sanitizer also can tell you, okay, not only that there was these concurrent writes, but it also knows where it was and can point you directly to this, in this case, Fortran code where the data race really happened. And then finally, we were thinking, okay, what was the developer's intention? Probably not the data race, but as I said at the beginning, the array was allocated such that it has 1 value for each thread. But when the array is basically passed to Fortran, it's only the pointer to the first element is passed to the Fortran code such that all threads access the same element basically. So what was actually intended is basically to pass a reference to the correct element for each thread. And if you pass that at this point in the code, then actually there was no data race anymore and the code performed deterministically as expected. And then what we also found out or recognized by looking at this code again was that what was basically implemented there using pthreads is actually an OpenMP parallel region. So we refactored the whole code to use or to basically make use of OpenMP parallel regions such that this whole loop which creates the pthreads is just an OpenMP parallel region, and all of this fork join mechanism is then basically automatically done by this implicit barrier inside the parallel region. And the result is, of course, that the application can now reuse the threads it creates. It will not create excessive number of threads anymore, but just reuse, for example, 8 threads all the time. And in addition, our group is also developing a tool which is called Archer, which is, let's say, an extension to thread sanitizer, such that thread sanitizer can understand these OpenMP parallel constructs, how they implement synchronization semantics and stuff like that. And also with Archer, we were able to basically detect the same data race as before. And then now that we had basically the data race free application, we can finally conduct our performance analysis that we wanted to do in the first place. And for that, we used the Scalaska tool suite, which consists of Scorpy, Cube, and Vampire, where Scorpy is basically the measurement infrastructure which collects the data. With Cube, you can get, for example, the screenshot here. Here you can see the whole call tree of the whole application that we executed, and with the different colors, it tells you basically where's your runtime mainly spent. And in our case, it's this dgmres main function, which we will see is basically this parallel gmres solver. And yeah, in this case, there's more than 70% of the whole runtime is spent in this GMRS solver. And what we additionally did is to calculate some fundamental performance factors, which I cannot go into much detail here. But what these factors told us basically is, is related to the load balance. And it showed us basically that the code seems to have load balancing issues between the individual threads. And there we had a deeper look into the code and then looked how this GMRS is actually implemented. And there's a numerical trick such that basically, the whole big system matrix gets, let's say, chunked into some smaller sub-matrices, and then each thread can basically solve a smaller independent GMRS problem in sequential. And we use then Vampire to visualize basically the execution of this parallel GMRS. And what we found there is basically, as you can see, that most of the threads, for most of the threads, the subsystem converges already after a little bit more than 30 iterations. But for a single thread, it required like, what was it, 46 iterations to converge. And while this one thread is computing, all the other threads are waiting and idling in this implicit barrier, which is of course not very efficient and leads to this load balance that we saw before. And our solution to tackle this problem was then to implement an approach that we just called a conditional nested task loop. And for that, we basically identified parallelizable subroutines in this whole GMRS procedure, which are, for example, computation of a matrix vector product, the DAXB operation that is known from the LAPEC package, basically. Also the residual computation, which determines if the GMRS already converged or not, is easily parallelizable. What's not easily parallelizable is the orthogonalization of the vectors that are generated during GMRS, which we did not parallelize then. And also we keep, what we did is basically we introduce a global variable and then just keep track how many threads have already finished with the GMRS computation. And if there are more than 75% threads finished with their work, we trigger our nested task loop. And then this is basically the result that we got, again, visualized with Vampire. So for the whole application, using this nested task loop, we got almost 10% speed up. And overall, the load balance increased by 15%. And what you can basically see is here down in this visualization that when our conditional nested task loop triggers, basically it will create tasks such that the idling threads can basically help the slower thread to finish these computations. I think that's all regarding that. And what we finally did is we also analyzed the I/O performance of the code, because CFD applications, they like to write lots of data in regular intervals to, I don't know, for example, for post-processing, for visualization, for other analysis. And in this case, we measured then the extreme case such that every time step gets written into a file. And what Darshan can show you, for example, is this diagram here. It can tell you, okay, what's the average I/O cost per process, meaning, what's the percentage of the runtime that is spent, for example, with read, with write calls. And for our case, what we can see here is that Calculix spent more than 20% of its runtime performing some writes, which is quite a lot, I would say. What Darshan can also tell you is that the exercises, how basically how much data is actually written each time a write or read call happens, was in this case only between 26 to 50 bytes, which corresponds to roughly 3 to 6 double precision values, which are roughly the scalar values that are stored on each mesh node in the simulation. And you know that HPC systems used to have a file system which is also connected via a network. So it's very inefficient to write small chunks of data to the file system, and it would be much more efficient to write larger chunks. And this is basically then the optimization that we performed. We modified all of the file open calls in the code and added this buffered equals yes keyword, such that internally the operating system will basically collect all of the data that should be written to file, and then decides if it has enough data to actually perform the write to the file. And the result was then in the end that now most of the runtime is spent computing, which is what we want. And also Darshan verified that most of the writes now write data chunks of almost 8,000 bytes, which is also good. And in the end, this lead to a application speed up of 1.43x for the whole Calculix application. And this brings us already to the conclusion. So first of all, if you want to conduct performance analysis of any code, you should make sure that the code is indeed correct and computing the correct thing. And for that, you can use tools like Thread Sanitizer or tools that are developed by our group like Archer and Must if you have an MPI code, for example. Also, all of these performance tools that we saw, they are very helpful to identify bottlenecks in your application that limit your scalability. In our case, it was this load balance issue and also the unbuffered I/O operations that were prohibitive. And also, the visualizations that all of these tools can provide. They help you to understand, not only to find the bottlenecks, but also understand these bottlenecks. And then if you have an idea how to optimize these bottlenecks, you can also easily verify that you indeed achieve the speed up with these tools. And finally, if you are interested in any kind of these correctness analysis, performance analysis, we are basically part of this POPs COE project where we offer exactly these kinds of services to academic users in the whole of Europe. There's a link where you can request these services, or you can also talk to me. And with that, I thank you very much for your attention. And if you have any questions, feel free to ask them.